Crude oil is very useful as it is refined into various petroleum products such as gasoline, kerosene and diesel fuel. However, the end product of crude oil consists of impurities such as sulfur, and it is very important to remove sulfur from the end product as it is very harmful for the environment. The process to remove sulfur is known as the hydrodesulfurization or HDS, and the figure displayed is a schematic diagram of HDS unit in petroleum refinery.
Next, we will now talk about the catalyst screening. Our team's choice of catalyst is the nickel molybdenum coated on aluminum zeolite. It is an acidic catalyst with the following general properties. In an experiment entitled Facile Ultra Deep Desulfurization of Gas Oil through Two-Stage or Layer Catalyst Bed, HDS was conducted by an autoclave type reactor. This figure shows the NH3-TPD spectra for all the catalysts used, and the highlighted part is for NiMoAz. This shows that aluminum zeolite supported catalyst has a larger desorption rate when compared to any other catalyst. Besides that, in the first state layer of HDS under SRGO, NiMoAz exhibits the lowest amount of sulfur left in the desulfurized product, where it shows that this catalyst has the highest catalytic activity amongst all the catalysts used. For the regeneration method, NiMoAz can undergo superficial carbon dioxide extraction, where this process includes a mixture of supercritical carbon dioxide and various polar solvents carried out in an experimental plant. A 6.9 weightage percentage decrease of the initial mass catalyst was reported, which indicates a prime potential for the regeneration method, which can be seen in the image below.
In this section, I will explain on reaction mechanism of desulfurization of crude oil fraction. These are the few mechanisms of reactions for hydrotreating reaction, ranging from different type of organic sulfur compound, from mercaptan, sulfides, disulfides, thiopene, benzothiopene, and dibenzothiopene. For adsorption mechanism, it is acknowledged that the research on adsorptive mechanism onto catalyst is minimal and hard to be retrieved due to the assumption that adsorption mechanism is not the rate determining step in our study. However, Wang et al. In 2004 has developed an equation for adsorption mechanism with the assumption of existing two types of adsorption sites on the surface of the catalyst, one on which the DBT and its product competitively adsorb, and the other is on which hydrogen adsorbs. For red law, we are using Otsuka et al. In 1960 studies equation, assuming the rate is first order with respect to the partial pressure of sulfur compound and the zeroth order to hydrogen. However, this assumption is further generalized to reduce the error in assumption. Next, we study the effects of temperature. A higher temperature gives a significantly higher rate constant. The activation energy was found to be approximately 60.34 kJ per mole. We are using Arrhenius equation to find this activation energy. The graph below shows the influence of temperature onto our reaction. As time proceeds, with increasing temperature, the sulfur content becomes much lesser in a faster time. Last but not least is we study the effect of pressure onto our reaction mechanism. A high pressure results in a faster conversion of reactant. As what we can see below, as we increase the pressure from 3 MPa to 5.5 MPa, the time to achieve 80% conversion in minute is much lesser, indicating that as we increase the pressure, the reaction becomes much faster.
Now, I am going to present the part determinations of reactor design by seeing the aspect pressure, temperature, and phase. Here is the schematic diagram of hydrodesulfurizations of crude oil. The compositions of the feed will include hydrocarbon, inert gas, and sulfur component. After this desulfurization process, the product will only left hydrocarbon and inert gas. The sulfur component will be separated out. The operation condition of each instruments are also shown in these tables. The crude oil will be pumped in by the pump in the liquid phase, and it will go to heat exchangers in the mixture phase. Then the crude oil will go into fire heater, reactor, cooler, gas separator, and vacuum distillations with those conditions. The catalyst that will be used inside the reactor is nickel molybdenum supported by alumina zeolite.
Now we move to reactors selection and design. For hydrodesulfurization of crude oil fraction, we choose to use trickle bed reactor, or simply called as TBR. TBR uses the natural downward movement of liquid and upward movement of gas over a solid catalyst as a working mechanism. For this reaction, we have the crude oil in liquid form, hydrogen in gas form, and catalyst in solid form. Trickle bed reactor will sprinkle the liquid to increase the efficiency of the reaction by boosting the surface area of the reactant. This is the diagram for a pilot plant of hydrodesulfurization of crude oil fraction. Simply focus only on the reactors, and we will see that it uses 3 reactors in a parallel arrangement. Below are the assumptions to be taken for the reactors. First is the velocity of gas and liquid passing through the reactor is constant. Second is no reaction in the gas phase. Third is the reaction pressure is constant. Fourth is it is surface reaction in mass transfer. The reaction only occurs on the catalyst surface. Fifth, no change in catalyst activity. Lastly, due to the negligible evaporation of HTCT under HDS conditions, organic sulfur can be considered non-volatile. Here are the reactor's parameters. The pressure is 14 megapascal, reaction temperature is 648 Kelvin, the catalytic bed length is 50 cm, the reaction diameter is 2.9 cm, and the liquid mass velocity is 3 times 10 to the power of negative 2 g liter gram over centimeter square second.
As we completed this project, we were able to determine the type, size, and shape of catalysts, reactor types, kinetics that were used, and prediction of ideal operating condition. The benefits of conducting this study is that the best reactor can be chosen for the contact between the phases and also the selection of optimum catalyst. The model is also validated with the presented complete data and has been successfully predicted the effect of various parameters for an optimum process of hydrodesulfurization.